Hello, Rick here, and welcome to video number 18 of Rick's Pipe Dream Magnetic Motor Generator Project Series. As you can see, I have my Husky digital level set up on the flywheel, and I'd like to turn that on at this time and see if we can verify that the setup is actually level. You can see the temperature of the room shows first 70 degrees. Okay, it's for all intents and purposes we can say that it is level. Yeah, there it comes. It's 0.0 degrees. It's right on the money. So that's all well. Now I've zoomed in here a little bit to show you something. On the edge of the wheel I've placed an arrow, a mark, on some masking tape with the number 1. You may not be able to see that. And then around here I've got the number 2 and another arrow, 3 and 4. There's 4 marks, and these correspond to the places where I need to move the stator arm over to the other pole. And it's always at the tail end of each group, as you'll notice. Tail end, tail end, tail end, and tail end. So each of these marks is 90 degrees apart. 4 times 90 is 360 degrees. Okay, I've zoomed out to get a better overall view of the wheel. And at this point, I'd like to clear up a couple of misconceptions that some people are having about exactly what's going on here. Now, all along through this video series, I've been receiving comments from people, some attempting to be helpful and others simply critics, saying that I really need to employ some kind of technique to avoid sticky points. Now, a sticky point is any point during the rotation of the wheel or the rotor where a strong attraction force occurs, which is strong enough to produce a counter-rotational effect. And let me just demonstrate that. As the north of the stator is placed directly over the south-facing up magnet group, it propels that group along, but when it reaches the back end of the group, there's no more propulsion, there's no more magnets out here. All the magnets have passed by to the other side, you see. And when that occurs, all the attraction is at the other side. Therefore, it wants to bring the wheel back in the opposite direction. And that's a really big problem when you have a stationary stator. And the only way you can get rotation then is to overcome that somehow, usually through the use of some type of magnetic shielding. Okay? Now, the other problem that one encounters with a stationary stator is repulsion forces that are strong enough to cause the wheel to stop rotating. Now I'll show you how that can occur. We'll come through the south group, and when the north group approaches the stator, see what happens? It's the brick wall effect. It slams into that wall where you have strong repulsion of north to north of the stator, north of the rotor group. It's very strong repulsion there, and it pushes the magnet group back the other way, changing the direction of the rotation. So both of these effects have the capability of stopping rotation. And people who use stationary stators have to come up with ways to overcome that. Typically it's done either with magnetic shielding or by using weaker magnets at those points so that those forces aren't quite as strong. Now with a moving stator design such as I'm using, I entirely avoid those sticky points and repulsion points that would cause a stationary stator setup to fail. And here's how it happens. Here's how I do it. As the I'll use the south magnet group now. Wait a minute. I'm going to use the north magnet, the north pole of the stator magnet, to draw in the south pole like we just did. But at point number 1 in the rotation, I rotate the south pole of the stator into play. This repels the south group, giving a burst of acceleration, and I'm already aligned properly to draw in the north group to get a further acceleration burst. This is point 2 now, and this is where I need to move the stator magnet again, bringing the north pole into play, which is repelling that north group further along in another burst of acceleration, and I'm properly aligned to draw in the south group of the next magnet group in a further acceleration burst. So each one of these acceleration bursts are additive, you see. Now, at this point, at number 3, I rotate again the stator, and this repels the south magnet group and leaves me in a position to draw in the last magnet group in the rotation, which is a north magnet group. Draws that in, and that brings us back to point number 4, which is where I rotate the stator once again and get repulsion and then attraction of the very last magnet group. All right? So what happens here is that I have rotated the stator 4 times, and it actually only needs to rotate a very small amount, about a ½ inch, and it only rotates at those 4 points that are 90 degrees apart, right? And so I'm rotating the magnet 4 times during one rotation, and yet I'm getting 8 accelerative bursts. And that's the beauty of the moving stator design. I entirely avoid negative results, and all I'm getting is positive reinforcement and additive accelerations at every point along the path. So you see, I don't need to avoid anything. What I'm doing is making full use and taking full advantage of every one of those forces. Now, what you should also notice is that the movement only occurs at those 4 points. That's the only time I move the stator, and I just move it a small amount. So I'm moving it within a distance of perhaps 10 degrees of the rotation at the tail end of each group. There's 10 degrees there, 10 degrees there, and so on. 4 times I move it in one rotation. Every rotation I move it 4 times through a space of about 10 degrees. Now, what happens during the other 80 degrees of that 90 degree separation? Well, what happens in that other 80 degrees is that the stator is not moving at all. You see, there's no force required to move it.